Thanks, Nir, and welcome. It's my pleasure to be able to introduce our second candidate for the lead scientist position, John Callaway. John is a professor in the Department of Environmental Science at the University of San Francisco, where he has been since 1999. He also spent a stint of time at the Pacific Estuarine Research Laboratory at San Diego State University from 1994 to 1999. Done a lot of work on wetland restoration in both of those areas. His Ph.D. is from Louisiana State University, completed in 1994. He worked with a very well and very renowned wetland ecologist, Bill Patrick, while he was at Louisiana State. He did his degree in the Oceanography and Coastal Sciences component of LSU. He did his master's degree at San Francisco State University in biology in 1990, and he has 2 bachelor's degrees from Berkeley in 1985. One kind of you might think of the more traditional pathway. He has a degree in biology, but he also has a degree in Slavic languages and literature, which he just told me included some study in Poland and also a focus on Russian. So interesting background. He has a very strong and sustained publication level, which I find to be quite admirable when you're at a university that mostly has a teaching mission. He's done a lot of really interesting collaborative research, and steadily over the last basically 2.5 decades. He has a very strong interest in focusing on science policy management interface. He's been on editorial boards of some of the key journals to which many of us look for information. So he's been on the editorial board of Ecological Applications. He's been on the editorial board of Estuarine and Coastal Estuaries and Coasts, and he's also been on the editorial board of Wetlands. He's also been involved in a number of interesting science advisory committees, both in San Francisco Bay, but also has worked a lot with people down in coastal Louisiana. And we heard during the Science Enterprise Workshop a lot about some of the work being done in coastal Louisiana, and John has certainly played an interesting advisory role there. He is program director of the University of San Francisco's graduate program in environmental management. This is a program that offers a master's degree program. We had a nice chat about it last night. Very successful program in developing people who kind of work, again, at that interface of environmental sciences and policy. And so with that, I'd like to introduce John. His title of his talk for us today is Understanding Mud and Carbon in San Francisco Bay Wetlands, Insights for Incorporating Science into Management. John.
Thank you, Cliff, and thank you all for being here. It's really nice to have the opportunity to present some of my research, and I'm really excited to be considered for the lead scientist position. As Cliff said, my work has really focused on wetland restoration, wetland management, climate change impacts on wetlands, and I have been working in the Bay since the 80s when I did my master's project on Spartina alterniflora. So I'm very interested to get more involved in management issues and to move upstream into delta issues. So I'm going to try to cover a wide range of topics and really introduce you to the range of research that I've been involved with over the last few years, focusing on mud and carbon, or plants, pickleweed that's illustrated there. I'm going to talk briefly about some other projects from the Pacific Estuarine Research Lab and my work in Louisiana, and also then finish up thinking about how some of that work has a link to some of the issues here in the Delta. So to give you a little background and introduction quickly, tidal wetlands are right on that margin of the ocean or the bay and the land, and at low tide they're completely uncovered by the tides. As the tide comes in across the marsh, they're flooded, and there's a strong inundation gradient from the low end of the marsh to the upper end of the marsh in terms of how frequently they're flooded. The flooding brings in water, brings in sediment and nutrients that are critical for the marsh, as well as many organisms, but it also creates anaerobic stress for the plants, and because of that you get a strong difference in the communities that you have there, and also a strong difference in elevation. In the upper edge of the marsh, it's really only on king tide events, like this is from China Camp in Marin County, It's only on these really large tide events that this upper part of the marsh is flooded. But so generally, wetland plants are very sensitive to elevation. Just a slight change of 10 or 20 centimeters can mean a change of plant community or a change of whether or not plants are even present. Because they're so sensitive to elevation, sea level rise is really critical because a change in the water, it's their elevation relative to the water that's most critical. And so as sea level rises, that will have significant effects on the plant community. And as you all probably know, sea level has been relatively stable over the last century, 1 to 2 millimeters of rise in the 1900s, but increasing towards the end of the decade up to about 2 to 3 millimeters per year over the last decade. And the bigger concern, of course, for wetlands is what might happen into the future as sea level starts to rise much more rapidly in the coming century. So if we think about that conceptually, the sea level rise or subsidence and compaction are driving down the elevation of the marsh relative to water. For most natural wetlands in the Bay Area, subsidence is not such an issue, but as you all know, in the Delta and in the Bay, diked wetlands, really subsidence is a dramatic issue and has big implications for restoration. But natural marshes are relatively stable in that sense, and so it's really sea level rise that's affecting them. And then the wetlands sort of counteract that sea level rise by building sediment. They can build mineral sediment that's coming in with the tides, and then they can also build organic material from their root and rhizome production. So that's the mud and the carbon that I'm going to be talking about through my talk. So if we think first about mud, the first question that I want to address is how quickly mud flats or restored wetlands develop sediment and accumulate sediment. And if you think about that in a general sense, this diagram shows you the hypothetical development of wetlands. On the left-hand side of the graph, you can see a steep increase. It's elevation over time. And so if a marsh is, or if a low elevation site is restored, it's going to build elevation very rapidly. It's flooded more frequently by the tides, so there's much more opportunity for sediment to move into the wetland. And then it slowly flattens out and asymptotes towards the mean high water, or the upper edge of the tidal range. And the vegetation establishes somewhere in between mean tide level and mean high water, probably a little bit closer to mean tide level than is illustrated here. So that's the hypothetical idea of how these develop. I had the opportunity over the last decade or so to evaluate and see what does this really mean for the salt ponds in South San Francisco Bay, where one of the big uncertainties, one of the issues addressed with adaptive management in the salt pond project was this question of how quickly they develop. So two areas, the island ponds, or pond A21 was the first area that was breached as part of the South Bay Salt Pond project, and then the Duckhead Pond, or A6, was breached a little bit later, and we followed each of those, A21 a little more intensively than A6. And at A21, since it was the first pond that was restored, we put out pins every 100 meters or so across the marsh, or across the pond, so that we could evaluate how quickly it was accumulating sediment. And this is out in the field. For those of you who know me, I don't usually give presentations in suits, but I also don't usually bring a sledgehammer out to the marsh to install my sampling stations. But there's this layer there of about 6 inches or more of almost concrete of gypsum that accumulated over 80 years of salt production. And to get through that, it took sledgehammers to establish our posts. We did pretty simple sampling. We knew there would be rapid rates of accumulation, so we just put posts in the ground and measured how quickly they're accumulating sediment. And this diagram just shows you, if you can't read the numbers in the back, the bigger the circle, the more rapid the rate of sediment accumulation. And remember that sea level rise currently is 2 to 3 millimeters per year. These sites developed hundreds of millimeters, 200 millimeters, 20 centimeters of material over a 3-year period. So dramatically more than sea level rise. They're rapidly accumulating sediment and elevation. And the dashed line that breaks the island up there is just because the north end of the island, above that large tidal creek, was at slightly higher elevations than the south end. And if we follow the site over time, you can see the averages for the northern and the southern area. The northern area developed much more slowly because of higher elevations, but the south part of the island developed at 68 millimeters per year, so 20, 30 times the rate of the current rate of sea level rise. So is building very rapidly, and it looks like that hypothetical curve that we expected. It's slowing down. And the site also developed vegetation. Because it built so quickly, it developed vegetation much more quickly than any of us expected. Within 2 to 3 years, there was a substantial amount of vegetation at the site. So then we wanted to see, would this happen again at the Duckhead Ponds across the bay and slightly farther north within the bay. We weren't able to put out as intensive of sampling, but we used the same simple methods, and what we found was even more dramatic rates. 200 millimeters per year over the first 2.5 or 3 years of studying at the island ponds. And that's also because, just as you might expect, it was lower in elevation than any of the area within A21. So really super rapid developments. And then we had the opportunity to go back just recently in the last year to reevaluate the sites and look at them after 10 years. What we found was that both of them continue to accumulate very rapidly. And what was most surprising to me was that A21, the red and black lines, actually isn't slowing down much and is still continuing to develop very rapidly, and so still really hasn't reached that point. And if anything, just the sampling at the 40-month period was probably just somewhat of an anomaly and slightly lower. So they're both continuing to develop very, very rapidly. So if we think about the implications of that, there is the opportunity to build elevation and sediment very quickly, at least within the South Bay of San Francisco. So the second thing to think about then is, how is that mud getting into the marsh? How is the sediment getting into the marsh? And in order to address that, I worked on a collaborative project with Jesse Lacey and Matt Ferner from USGS and the San Francisco Bay National Estuarine Research Reserve. What we wanted to see, this was at China Camp in the North Bay, we wanted to see how is the sediment moving into this, not a salt pond, but a mature marsh. And most people and many other locations, people have shown that it's through the creeks. The water comes in with carrying the sediment through the creeks, and then that floods over the marsh, and the sediment is delivered that way. And that's what we expected. But the other possibility is that the sediment is coming in across the bay wetland or the mudflat wetland interface, and rather than through the tides, coming in directly from the bay. As I said, our expectation based on previous observations was that it was coming in through the creek, so we started all of our measurements in the creek. And Jesse measured suspended sediment and water depth and currents both in the creeks, and then she had a number of stations off the edge of the marsh in the bay. And then we added in the second and third year stations with a transect across the mudflat so that we could see how much was coming in. And then Matt and I were collecting water samples on the marsh on king tide events when the marsh was really flooded to see what the suspended sediment concentration was right on the marsh surface. I'm going to show you Jesse's data. And what she and her colleagues did was they put out these instruments, as I said, that could measure flow rates and turbidity. This shows you some of her data. The top graph in blue is the water elevation. The green is the water flow or velocity, with the negative value meaning out of the channel and the positive value into the channel. And these were set up and monitored over about a 1.5 to 2 month periods in the winter on the around king tide events, and then again in 1 year on the summer. I'm just going to show you a bit of data from 1 year sampling. And then the black lines are suspended sediment concentrations, and if you put together the velocity and suspended sediment, multiply those together, you get the flux or the total amount of sediment moving in and out of the marsh. What we found was that the flow rates on the ebb tide were extremely strong and high, and what we think is happening is that the water is actually coming in over the bay front, but then draining out through the channels. And as it drains out through the channels, it carries with it a lot of sediment. So in fact, in this case, the creeks are pulling sediment out of the system rather than delivering sediment, which was definitely a surprise. And not only pulling it out, but a very significant amount of sediment is coming out of the creeks, probably eroding from channels. It's not eroding the marsh itself, but eroding from channels and pulling that out. So at least at China Camp, the creeks are really not delivering the sediment. So like I said, we set up some additional sampling in the following years, both in the winter and the summer, to look at the transport of sediment across the marsh, the wetland mudflat interface. And you can see this transect going from the bay on the right side with an increasing elevation through Spartina, and the transition zone is the Spartina pickleweed transition, and then across the marsh plain with pickleweed areas. And we had similar instruments, not measuring flow, but measuring water level and turbidity, and the similar collection of samples right on the marsh using these little sample bottles. And what we found here was that this shows you the suspended sediment concentration on calm, moderate, and windy days with big waves, from the bay on the right to the mudflat transition, the Spartina in the red box, and then the marsh plain and the channel. And what we found consistently was that the suspended sediment concentrations are extremely high right at that mudflat Spartina interface, and there is a lot of sediment being pushed up from the mudflats into the marsh on the high tide event. So it's contrary to what we expected. The creeks really aren't delivering much sediment. They're actually exporting sediment. And it's the wetland mudflat interface, at least at China Camp, that's most important. So obviously that's just this one location, and we need to look across a mix of areas. But it does have big implications if we think about how we might sustain marshes. And I'll talk about next that marshes really are keeping pace with sea level rise. So right now we don't need to do anything to augment sedimentation. But I've been working as an advisor for the Corps of Engineers, working with Jeremy Lowe at San Francisco Estuary Institute. We're also working with the Corps and with a number of other scientists to give input on how might we go about augmenting sediment in 20 or 30 or 50 years when wetlands begin to lose elevation. We could pump sediment into the marsh and spray it on the surface, as has been done in Louisiana and Venice and many other areas. We could pump sediment into channels and let it be spread from the water column in the channels, or we could dump sediment offshore and with the shallow placement method at the bottom of the slide and allow natural forces to carry it into channels or across the marsh mudflat interface. People didn't really think much about these shallow water placements, and there's still a lot of uncertainty about using them. But I think from our data, that's a method that we might consider. And so the Corps is now in the process of developing some preliminary experiments to see if you do that, how much of the sediment you dump actually does make it into the marsh. And so I think the plan is over the next 5 to 10 years to start doing some of those experiments so that when wetlands do start to lose elevation, we'll be ready and we'll be able to identify what some possible management alternatives really are. Okay, so for the last bit in talking about mud or sediment, I'm going to talk about accretion rates and just how quickly natural wetlands are building sediment, and are they keeping pace with sea level rise. And this is work that I led at USF, but did with colleagues from LSU, Gene Turner and Charlie Milan, and Evan Borgness was at USGS at the time. What we did was collect samples from 6 different wetlands around the bay to try to see what the variation in accretion rates were across different wetlands. It included salt marshes that are in red, brackish marshes in Sassoon Bay like Rush Ranch and Browns Island, and you can see Coon Island is sort of doesn't know whether it's a salt marsh or a brackish marsh. It's really a hybrid with a mix of vegetation and a mix of characteristics of the two. So at each place, we set up transects so that we had, this is at China Camp, we set up transects so we had samples from the low edge of the marsh up to the higher edge of the marsh, and 2 transects at each site. Of course, it would be great to have 5 or 6 transects, but it costs about $3,000 to $5,000 to run each core, and so we were limited. But we felt even with 6 samples, we ended up with dramatically increasing the coverage that we have in understanding for accretion rates. In order to measure accretion rates, we collected a 50-centimeter deep sediment core that we then sectioned. That shows you a core laid out on a little tray, and we'd section it every 2 centimeters, and then look at, use 2 different radioisotope methods, cesium and lead-210, to evaluate accretion rates. Lead-210 goes back about 100 years. Cesium goes back 50 years to 1963 when we were crazy enough to be testing atomic bombs in the atmosphere, and spread cesium throughout the northern hemisphere. The one great side benefit of that was provides a great dating marker that we can evaluate our marshes. It's luckily, it's at very, very low levels. You need a pretty sensitive instrument. You're not digging in the soil or the mud. You're not exposing yourself to any significant radioactivity. But what we found was that accretion rates across the bay averaged about 3 to 4 or 5 millimeters. So wetlands currently are definitely keeping pace with sea level rise of a few millimeters per year, and are even maybe slightly more. Whale's Tail down there in the South Bay with 6 millimeters is the youngest. Most of the marshes, these are thousands of years old, but Whale's Tail is probably just 100 years old or so, and also is at slightly lower elevation, so as you'd expect, is accreting at slightly higher rates. If we look at those data in a little more detail, this shows you from the bottom to the top of the graph, the salt marshes at the bottom going up to the brackish marshes at the top, and then from the left to the right, the low marsh locations, the mid and the higher elevation areas. And as I said, you know, there were, prior to our dating, there were 3 cores collected in the bay, actually by Bill Patrick back in the 80s. And so we went from 3 cores to 37 cores, or 40 cores total. So much greater coverage, and actually now as good of coverage as in many, many other places around the country. What we found that was somewhat surprising to me was there wasn't a lot of variation in accretion rates. And pretty much, if you look at the marsh plain, the mid and high marsh elevations, they accumulated almost all of them, something close to 3 millimeters per year. And you can see the black bars indicate the cesium dates over 50, an average of about 40 to 50 years. The gray bars are lead-210 over 100 years. The lead-210 rates are always lower because that sediment, as it's there, consolidates and compacts. And so if you measure over a year, you may have a really rapid rate, but over 100 years, that's going to be much, much less averaged out. But still, most of them are, either way you look at it, are building more than sea level rise. And then in the low marsh, some of the sites are building more rapidly, 5, 6, maybe even up to 8 millimeters for some individual cores. And that, if anything, gives us some optimism that marshes are somewhat resilient and are likely to be able to tolerate some increases in sea level into the future. So are they keeping pace with sea level rise? Definitely yes, they are keeping pace with current rates. As I said, the bigger question is into the future, how will they respond as sea level rise increases significantly? And I didn't include any slides, but I'm sure all of you are aware of the work that Dave Scholhammer and his colleagues, others at USGS have done, that sediment concentrations and inputs to the bay are decreasing. That's not good news for our marshes because they do need more sediment to continue to build. So you know, that's something to be aware of and definitely has implications, like I said, for how we might manage marshes into the future. So to summarize what we've learned in terms of mud or sediment, restored wetlands definitely can build elevation very rapidly in San Francisco Bay. That wetland bay interface plays a more important role than we really thought, and we really should think about how we might use that for management. And wetlands in San Francisco Bay are keeping pace currently with sea level rise, although into the future there may be more to think about. So if we think about what that means for management, if we're interested in building wetlands, we should restore them sooner rather than later. We need to build those elevations now so that they get to relatively high elevations when they'll be more resilient to sea level rise. We need to consider a mix of sediment delivery options. And for this, I mean for natural existing wetlands, not for restoration. For restoration, we need to just get the sediment in there you know, directly to those systems. But for natural wetlands, you can't pump sediment in like that or you'll bury all the vegetation and the clapper rails, and that's just not going to be viable. So you need to do it in a much less impactive way. And then we really need to manage sediment as a resource. And I think in the Bay, there's great awareness in the last 10 years that this is happening, and you know, the interest in these experiments or the interest in much greater interest in reusing sediment really reflects the fact that sediment, people see now that it's something to think of as a resource. Okay, so now I'm going to shift gears and talk about carbon issues, sort of related exactly to what I just talked about in terms of accumulation or accretion rates. It's not just the mud that's important for the building of elevation. For the marshes, in fact, it's probably more the organic matter. So if we think back to our little hypothetical diagram, In the early phase of the development of a wetland, it is all about mud. There's no plants there to contribute organic matter, and it's really just the sediment that's driving how a marsh develops or how a tide flat converts to a marsh. But over time, when the marsh gets close to that high elevation range, it's flooded very infrequently, and there's not a lot of sediment input to it, and it really is much more the organic matter that's probably driving how the marsh is able to keep pace with sea level rise. And I turn to this slide from Gene Turner, my colleague who worked on that project. He compiled a bunch of data from sites all around the country, actually all around the world, and what he did was he tried to see if you do a correlation between the organic matter accumulation within a location and the accretion rate, or the mineral matter accumulation and accretion rate, which one is more tightly correlated? It's just a correlation, it's not cause and effect. But what you see is there can be a large scatter of mineral matter and no real increase in sea level, in accretion rates, and that's because it affects the density of the soil, but it doesn't cause the soil to actually build more rapidly if you dump a lot of sediment on it. But a strong correlation with organic matter. And most people working in the, in my area of looking at sediment accretion and marsh dynamics really feel that the organic matter is really probably what's driving. It creates the structure of the soil, and really probably what's the more important of the two. So we also looked at the simile in our San Francisco Bay cores, and we found pretty similar results. The dashed line is the regression or the correlation from Gene's cores, Gene samples from around the world, and the solid line is for our individual cores around the bay, and all the different colors are the different sampling locations. But we found a very, very tight relationship between organic matter and vertical accretion that really confirms, I think, that idea. And if we think about that for brackish marshes and for our freshwater marshes, they are very productive, and I think they have the ability, they aren't so dependent on mineral matter inputs, and in that sense may be more resilient to future sea level rise. Okay, so then to look more really directly at the carbon within the soil, the motivation for this experiment, or the research that we did measuring accretion, actually was to measure sequestration rates. And that's because people have known for a long time that tidal marshes accumulate a lot of carbon, but there was very little data from San Francisco Bay actually quantifying that. And this data comes from a synthesis that Gail Chimura put together. She collected data from across the world, all of the dated estimates of sequestration that she could accumulate, she and her colleagues. And you can see a wide range of values here, anywhere from just under 100, 50 to 100 grams of carbon per square meter per year, up to about 600 grams of carbon. And so you also see only 3 cores or 4 cores from the Pacific coast. Those were those few from San Francisco Bay that were collected in the 80s. And so we wanted to see, where do we really fall within that range? We used the exact same study, as I mentioned, where we collected cores, those exact same cores, the exact same dating methods, but then we combined, instead of just looking at vertical accretion rates, we combined those vertical rates with sediment characteristics, organic matter or carbon content, and the density of the soil, and then you can convert the vertical rates to mass rates of carbon over time, using both lead-210, looking at it over a 100-year or a 50-year period. Oh, sorry. And what we found across the bay, if we look across the average across all of our sites, this is based on the 50-year rate using cesium, about 100 grams of carbon. The one site that was slightly higher was Browns Island with about 150 grams of carbon per square meter per year, but right in that sort of ballpark. And then if we look at the more detailed data from all the sites across all of the elevations, we found that the average was 80 grams of carbon using lead-210 and about 110 using cesium. And again, Browns Island definitely was one slightly higher site. Not such a strong pattern, a little bit higher rates at the low end over short term, again, because those are accumulating slightly more quickly, and as they build elevation, roots and rhizomes are going into those. The lead-210 rates are definitely lower. As I said, not only is the soil compacting, the organic matter is decomposing over longer time periods, and so some of that organic matter that accumulates over the short term is lost. If we look back to the broad range of estimates around the globe, you can see that our data really fit pretty much within the range of most of the other sites, of 100 to 200 grams. Those are all the individual cores that we collected. The sites that are slightly higher, that are above 200 grams or more, come from a handful of locations. Louisiana, where the land is subsiding rapidly and marshes are building at really rapid rates to try to keep pace with that sinking and building a lot of organic matter. Chesapeake Bay, where the similar conditions are occurring in some parts of Chesapeake Bay. And then from the Bay of Fundy, which has a much larger tidal range and also have the opportunity to build very rapidly. So I think those are really the anomalies. And the average rates that many people talk about from Gale's synthesis was about 200 grams as a global average, which I think really is an overestimate because it incorporates those anomalies, and it's probably much closer to 100 grams or 150 at the high end that those are accumulating. The unfortunate news, if we think about, this was all motivated, this research was by AB 32. People wanted to know, is there enough carbon in these accumulation in these systems to create incentives for carbon credits and for restoration? What we found at the current price of carbon of about $13 a ton, you can make about $20 to $30 an acre at 100 grams of carbon per year. So it's not a significant incentive currently, unfortunately. I think we need, hopefully the price of carbon goes up and it creates more of an incentive, and we also need to think about carbon more than just sequestration, but the potential protection of wetlands and reduced loss of carbon if the wetlands erode. But that was one thing that we found out that I think most people may not want to hear, but is the unfortunate truth of carbon pricing. Okay, so the last thing to think about with carbon that I'll present is sort of connecting this work up within the Bay into a much larger network of understanding carbon dynamics around the country. And this is work with Lisa Marie Wyndham-Myers at USGS Menlo Park and many other PIs. There's almost 20 of us working together, a mix of people like me who do soil and wetland ecology in the field, and then a bunch of remote sensors. The idea is to look at a small number of sites. We have 6 locations, 2 on each coast around the U.S., where we have really intensive data. Especially we have a number of dated cores. I've been involved mostly with the San Francisco Bay site, of course, as well as Louisiana, where but there's also Chesapeake Bay, a site up in Narragansett Bay, and up on the Florida Everglades, and a site up in the Puget Sound. Each of those we have really good data where we know pretty much what's happening with carbon. We also have some data on methane or other issues that are occurring, carbon issues. And then we're trying to take those data, take those sites where we have really extensive data, combine them with broader data around the country for soils data, from satellite data to look at above ground biomass and see how if that's correlated with sequestration rates. Also looking at soils maps, at elevation maps, at the boundaries of wetlands, and then sort of project the data around the country so that the current estimate of the national rates of carbon sequestration are as simple as take that average of 200 grams carbon, multiply it by the acreage of tidal wetlands in the country, and that's what the tidal wetlands are accumulating. And clearly that's way too crude of a simplification. So what we found is that there is a fair amount of variation from location to location, depending on productivity and decomposition rates and other things. So I think we've made some good progress in improving the national inventory, and hopefully this was a 3-year project funded by NASA to use their remote sensing data. We're hoping to get enough funding for another 3 years so that we can look at other issues, some of the more challenging issues that came up in improving our estimates over this first sort of preliminary project. So to summarize from the carbon studies, Organic matter really is critical for wetland accretion. Although mud may be driving a large part of the wetland development, I think it's organic matter that's most important over the longer term. Wetlands in the Bay are accumulating substantial amount of carbon, similar to most of the other wetlands around the country. And the national inventory really is moving forward and will substantially improve past estimates of carbon stocks and of fluxes. And really this was motivated by improving the inventory so that the U.S. could cooperate with the Paris Agreement and provide an estimate of what our carbon inventories are as part of that agreement. And hopefully there will be continuing interest in that into the future, but who knows with current funding and current interests. We think about management for those carbon issues. Again, it's more reason to restore wetlands now. Not only do we want to build the mineral sediment, but we need to start building, get them to where the plants are established and the plants can start building that elevation, and also are healthy and productive, because the more productive they are, the more organic matter they're putting into the soil and the more resilient they're going to be to sea level rise. As I said, unfortunately, current prices for carbon are too low to create much of an incentive, but hopefully that will change into the future. And brackish marshes, in part because of their greater productivity, might offer, if carbon prices go up, I think they probably offer the best opportunity for carbon sequestration in terms of credits or otherwise. And also they don't have the methane issue that freshwater wetlands are likely to have. So now in just the last bit, I want to talk about two projects that I've been involved with. One long ago, back in the past, down at Tijuana Estuary in the Pacific Estuarine Research Lab, and then about some interaction and science advisory projects. But first, thinking about the Pacific Estuarine Research Lab, we did work throughout San Diego, Tijuana Estuary being one of our key sites, and a site where there were great opportunities to do adaptive restoration, incorporating experiments into restoration projects. And I'm going to talk about two of them: the tidal linkage in the north arm of the estuary, that was the first of these two projects and a little bit smaller in scale, and then the model marsh in the south end of the estuary. The distinctive line that you can see across there is the U.S.-Mexico border. The city of Tijuana is just on the south edge of that, and that's the Tijuana River that flows through 3/4 of its watershed is in Mexico, and then it flows north and into the ocean. It's significant issues in terms of water quality and other environmental problems, but it's actually one of the more pristine wetlands in Southern California because there isn't a freeway going across the front of the marsh, and so it's relatively low impacted down in that tiny little corner of the U.S. And there's been a lot of research done there. It's part of the National Estuarine Research Reserve Program. So the tidal linkage was an experiment where there was work to provide restoration. It's called the tidal linkage because it connected up two tidal channels, and was a small-scale restoration, sort of a combination habitat and demonstration project, because it's right next to the visitor center, which is that building with all the trails around it. What we did was, this was work with Joy Zedler and Gary Sullivan back 20 years ago, but what we wanted to ask was, if you're restoring a marsh, is it important to restore a diverse marsh, or if just any old plants get established, is that enough? We wanted to see how diversity affected function in those three ways: vegetation structure, biomass accumulation, and nitrogen or nutrient accumulation. There's 8 species that we planted in a whole mix of different combinations of 1 and 3 and 6 species. What we found was, definitely in the short term, function is strongly affected by biodiversity. One of the unexpected results was, over the long term, the biodiversity actually declined in some of our planted plots. It still had an effect, but it was a more muted effect over longer time periods. So one thing I think we learned from both of these experiences was expect the unexpected. I mean, things don't always work out as you envision, and be prepared for those unexpected results. The second experiment we called the model marsh, and it was designed, as you can see, with these creeks. This was a much larger project. It was about 6 hectares or 20 acres, and the entire site was developed with a goal of setting up this experiment and evaluating evaluating the importance of tidal creeks in creating physical heterogeneity, and does that physical heterogeneity affect the way the marsh functions in terms of plants, sediments, and other and invertebrates or fish. What we found that was expected was there was an effect on plants and sediment and on invertebrates as well. Not as on the plants, at least, not as dramatic as we thought might occur. But the unexpected was that small-scale heterogeneity, tiny little ponds or low spots that developed within the marsh just with wind waves or other things, actually was also very important. So heterogeneity on a mix of scales, big creeks and tiny little ponds, created very different opportunities for invertebrates and fish and really affected the overall ability of the marsh. So I think here the take-home messages are incorporate experiments where you can, but be prepared for the unexpected. So then lastly, to think about other projects, I have been involved with a number of science advisory panels, many in the Bay or in Southern California as well, but also in Louisiana and Venice Lagoon, which is a great place to go work and learn about wetlands. I highly recommend. But I want to highlight the work I did in Louisiana. And there, as many of you know from the Enterprise meeting or from other work, there's a huge effort to restore wetlands in Louisiana, and they've been, over the last 10 years, every 5 years they develop a master plan. And they use models extensively, as I'll show you in just a second. And so I've been involved for both master plans to give input on how models are used within the master plan. For the most recent, the 2017 master plan that just came out, I was the chair of that with 4 other colleagues that we gave input over the last 3 or 4 years with the models. And this was all done with Denise Reed, who many of you probably know since she's worked so much here in the Delta and was part of that Enterprise work. So these are Denise slides, and I thank Denise for allowing me to use them. So like I said, I think you probably all know Louisiana is losing wetlands at a really rapid rate. This shows you about almost 2,000 square miles of loss over the last 80 years, and all throughout the coast. Just as we're concerned about sea level rise, they're even more concerned about sea level rise. That shows you sea level rise. If nothing is done, and that's over the next 50 years, not the next 100 years. And so the coast of Louisiana will change dramatically if sea level is even remotely close to what many of the predictions are. And so, of course, the state is very interested and very eager to try to do something to counteract this. So they've proposed, in order to prioritize where to spend their money and where to do restoration, they've looked at hundreds of projects. And you probably can't read that at all from the back, but if you see all those black dots, those are projects that were evaluated, that were considered for potential funding through the master plan over the next 5 years. And the model was used to evaluate for each of those, if you restore those, how much of a benefit are they going to have in terms of creating wetlands, providing habitat, reducing storm surge. And that was done with a model that really, I think the true lesson I learned from this model was the model in this case was very effective because it was answering a pretty specific question. Really it focused on wetland development. How do wetlands develop? The nutrient component of it was really crude, but the sediment delivery on a local scale is pretty crude, but on a larger scale it really illustrates, or it simulates how sediment moves into these wetlands and how they build elevation. So it's driven by what they called an ecohydrology model, which is a flow model that delivers sediment into barrier islands, into wetlands, builds elevation, it simulates subsidence and sea level rise, and then as the wetlands build elevation and salinity changes, that determines what sort of vegetation you're likely to have in the wetland. And then they use habitat suitability indexes or other models to see, okay, if you have that kinds of vegetation, how many oysters are you going to support? How many fish can you provide? How many alligators are going to live in your wetland? And they had about 20 different species of interest that they looked at. And then, as I said, they also looked at, if you have those wetlands in place, how much of a reduction in storm surge might there be, and how much flood risk reduction where there'll be in different parts of the coast, so that they can go to the legislators and say, if you're going to spend millions and millions of dollars on coastal restoration, this is where you should put the money, and this is where we see that it's likely to have a benefit. So with that, then I want to just finish up talking about connections to the delta and thinking about, in terms of science connections, I think in terms of my research or my interests, the wetlands in the delta, they're different than bay wetlands, but most of the processes are very similar, with the one caveat that, as I said, freshwater wetlands are much more dependent on organic matter and much less dependent on mineral matter in keeping pace. In that sense, that might be good news. With the reduction in sediment is not as likely to have as big of an impact on delta wetlands as it will within the bay. And in terms of other issues, there definitely are large opportunities for carbon accumulation in delta wetlands, with the one big caveat of methane emissions. If they're accumulating carbon but emitting methane, they may actually not be, in terms of net greenhouse effects, may not be so positive. But I think there's still lots of work. There's a lot of ongoing work looking at those, as I'm sure many of you are aware of. So thinking about how that science applies to the delta and the management issues, as you all know, there's all kinds of challenging science and management constraints or competing interests, including climate change, that I think maybe overrides or is, sets the framework for what we will do into the future. And I really liked the recent paper that the 4 lead scientists had that said that the delta is not just a wicked problem, but a devilishly wicked problem. And really, there isn't an answer. There certainly isn't a simple answer, and there isn't really any answer to solving all the problems, but there's a better way or a worse way to go about it, and what we need to do is use science to give us some guidance. So in terms of thinking about management issues, I'm preaching to the choir for sure. Adaptive management is the way we move forward, and incorporating science into management is really what has to be done in order to make some progress. I think from the South Bay Salt Pond projects or other things, the sooner we act, the better. We need to really improve our understanding and try some manipulative experiments. So I think incorporating experimentation into management and into our restoration activities is really key. We really need to think about what the key uncertainties are and then design experiments to address them. And as we were talking about in the interview earlier this morning, in Tijuana Estuary there were some relatively constrained questions to ask, and so it was easier to design experiments. In the delta, the challenge is all those competing issues and how do you tease them apart, and then even more importantly, how do you look at interactions of all those competing factors. And then lastly, I think models definitely can be a very powerful tool, but as I said, you really need focused questions, and you also need data to calibrate your models, and so that could be a limiting factor for some sorts of modeling. So just to finish up with some general conclusions, I think mud and carbon both are really critical to building restored wetlands and to sustaining existing wetlands into the future. They both play a critical, important role. Wetlands are keeping pace with sea level rise currently, so it's not like they're not going to disappear immediately, and they're not even going to start disappearing in the next decade. It's a longer-term thing, but we really need to start preparing about how we manage wetlands, how we might augment sediment or promote elevation gain and sequester carbon into the future. And then, as I said, I think collaborative science, all the work that I've been doing really has been work that either I've been leading with other colleagues or collaborating as a joint PI with others who are leading. I think that's really the only way to address many of these complex issues. And adaptive management, that's the way to keep moving forward, both for our understanding and for our management of the delta. And then I obviously want to thank all of my collaborators on many, many different projects, funders, and well as the agencies that have provided enormous support and access and ideas in terms of management issues for the work I've done. So thank you, and hopefully there's time for questions.
Definitely have time for questions. Yeah, we have a couple questions.
So you focus on funding for the experimentation. How about funding for the ongoing adaptive management, monitoring, et cetera. One of the things that I think we've all been frustrated by is setting aside areas for restoration and then not having funding for consistent monitoring and management. For instance, in the Sassoon Marsh, it's become a real problem.
Yeah, so, I mean, like we were talking about earlier this morning, I think you need to convince people of the benefit of that monitoring data so that although it may cost a little bit more upfront, if it can improve the way that you design restoration or the way that you spend your money in the long term, hopefully you're able to convince people that that's a good way to spend money. Definitely, you know, people like to see action. They like to see projects going forward and bulldozers out there moving earth. But I think that's our job as scientists and as managers to convince policymakers, convince people who are providing the funding. I think I mentioned the Louisiana project, and I said this earlier this morning. I think they're, you know, they put about 10% of, they have a, separate from the oil spill money that's providing funding for new restoration, they've had a lot of money over the last 20 or more years from the Bro bill to provide restoration of Louisiana projects, but they put about 10%. They have a set amount. If it goes into a project, they have to put aside money for current monitoring and for ongoing monitoring in the future. And they built a network of water quality stations, of sedimentation stations, of vegetation transects, so that they actually have a great network now that goes right into that modeling. And so I think it's absolutely necessary, but it's not simple.
Hi, John. Enjoyed your talk. Thanks, as always. I'm going to get philosophical on you here,
okay,
if you'll allow me. I was struck by the slides you had of Louisiana, the degree to which subsidence is going to really be something that they're confronting there. And, you know, I think one could talk about similar challenges here. And as an Estuarine ecologist and a tidal marsh guy, you know, you're by default a geomorphologist. Is there any notion that you would like to explore, you know, issues of abandonment of areas of the country that are just simply confronting so much cost and so much risk with sea level rise and climate change that maybe, you know, there's another strategy, and that's called, you know, get the heck out of the way kind of thing? Anyway, just interested in what your thoughts are on that.
I mean, I think that's easy, you know, so philosophically, of course, yes. In actual implementation, it's a challenge. In Louisiana, there are a few communities where they've put federal money into relocating people and moving them from those really high-risk areas, and but it's been very controversial. And not everyone has agreed to it. Even some of the people, even if you offer them money, still want to stay where they are. But I think it's definitely in Louisiana. It's certainly worth considering. And then I think here the other thing to think about is, you know, prioritizing where you're going to do restoration or where. We're not going to restore every delta island back to a super high elevation tidal marsh. It's unrealistic to think that. But what we need to do is prioritize and say, okay, where are there opportunities? How could we maximize the amount of tidal marsh in important areas, and then maybe other areas we do give up and they become, you know, or maybe we keep them diked and if we're willing to spend that, pay that cost.
Do we know where the mineral material in San Francisco Bay is coming from?
I think, well, so work that's been done at SFEI has shown a large, of course, an enormous amount of it is coming from the Sacramento-San Joaquin, but more recently people have shown that some of the local watersheds are actually delivering a significant amount of sediment. I think up to 50% of the sediment in the South Bay is coming from local watersheds. Which was a surprise to many people, but there is more and more data on that, and it's definitely a mix of sources.
Thank you for that interesting talk. Given, I mean, I think you hit the nail right on the head of the complexity of the challenges in the Delta. And when we see these examples from elsewhere, the ability to get to sort of a narrow set of questions to use as a pathway forward to use science to help inform management, how would you go about addressing that complexity for the Delta, and how would you identify the narrower set of questions to get started on?
I think just as the Science Office has been doing, you know, seek input from both a mix of scientists and researchers as well as management staff on I think there already are some obvious questions that are out there, but then in terms of prioritizing, it's look to the broader audience of people engaged in the Delta and get their input. And they're certainly not easy questions. Everyone wants to see, you know, everyone has their issue that they feel is more important, but I think we need, through some consensus, or maybe not consensus, but at least majority, we can identify prioritization and then get outside review as well. I think, you know, the Independent Science Board or the use of outside reviewers is super useful to get different eyes in terms of what we might want to try to put money towards.
I have two questions about the carbon sequestration work. The first one is, what percentage of the total primary production ends up in sequestered carbon? You were getting numbers of 100 grams of carbon per meter squared per year. Is that 5% of the production, 10% of the production?
It's probably 5 to 10. You know, most of our marshes, but probably 5 if you think about, because most of our estimates of production are above ground and don't incorporate below ground. We almost always just measure above ground because it's so hard to measure below ground. And most of the estimates are 1,000 to 1,500 grams, somewhere 500 to 1,500 grams of above ground productivity. So if they're producing the same amount below ground, you know, 1,000 to 3,000. So yeah, 5 to 10% or less even.
And the second question along that same topic, only looking at your national survey, I was struck by the lack of latitudinal gradient on the east coast of carbon sequestration. It seemed like to be just as high up in New England as it was down in Florida, and I was kind of curious about that.
I think, you know, I don't know. The high elevation New England marshes are really like peat marshes. There's hardly any. They're extremely high in the tidal frame, and they're just slowly building carbon. One recent project that I didn't have a chance to talk about but that I've been involved with a bunch recently is with Jim Morris, who's a modeler, and Jim and I and others. So actually, I didn't mention the model. I've done modeling of looking at sediment or wetland elevation over time and how much carbon is incorporated as a wetland builds if you model it. And Jim also has been doing similar work. And what we found, if you want to look at it in a simple sense, if you want to estimate carbon sequestration in a wetland, all you really need to know is the accretion rate. And it's the accretion rate times the density of carbon, which is amazingly constant across wetlands all over the world, really, because there may be a difference in bulk density of the soil, but it's the mineral, it's the mud that's changing that, and they build very consistent amounts of carbon. And so that if they're stable, they're building something close to 3 millimeters times the density of carbon, which is about, I forget the units, but it ends up being about 75 grams of carbon per square meter per year is what you'll build at 3 millimeters per year. And that is right where many of those marshes fall. The ones, like I said, the ones that are building a lot are the ones where subsidence is sort of creating the opportunity for them to build more into the future. Thank you.